Transform your optical design process. Go from concept to sales in record time with Zemax Virtual Prototyping from Zemax.
So with that introduction, I'll just say a little bit about myself, and that will be very quick, and we'll get into really the topic at hand here. I've been in the career of optics my whole career, and I have really enjoyed working on a variety of different systems, from imaging systems, laser-based systems, LED illumination, and so forth. This particular topic we'll discuss here, which was a feature released in 2017. Very quickly, I started using this for some projects and found improvements, but never really took the time to actually do an analysis of any savings in ray tracing speed or any savings in getting to a solution. So last fall, I put together this material for the Zemax Envision conference, and I'm happy to present it again here today. So with that said, let's move into the topic. So we'll look at contrast optimization as a method for optimization of imaging systems, both how it compares to other methods, both traditional optimization methods, and then I also took the liberty of comparing it to some competitive software, to Zemax opticstudio, just to provide a little bit more balance and fairness to the analysis and comparison. And then we'll look at some examples of what those might be, and then take some questions at the end. And just as a reminder, if you have questions as we go along, put those into the chat box. Robin will be collecting those, and we will address those at the end of our time. So we'll look at contrast optimization, and the presentation is actually a little bit in reverse. We'll give you the answer up front, and then we'll look at how we arrived at that answer and some of the details behind the system that I put together and optimized practically. So why contrast optimization? Well, it is more targeted. It's looking at cutting off the spatial frequency that is set by your image sensor. It is faster slightly, but more importantly, you get a better result than with other methods. Again, this is with one particular system, but I've seen this work in other systems. I just haven't collected the data like this for other systems. So we'll look at the conclusions again right up front, but then we will actually go into what were the requirements for this test imaging system. We'll also look at tolerancing, and this will be taking a different example for tolerancing to show that, but also look at expanding the base design a bit further, and kind of compare those together. It's pretty interesting. So with that said, let's jump into contrast optimization. This was developed, as I said, in 2017. With the idea to target image systems that have a discrete image sensor, and by the Nyquist frequency, there's a limiting resolution because of the pixel size. So with that in mind, the math was all constructed to then build a new default merit function that can be added to your design and then used either by itself or in conjunction or back and forth as you're working through your system. From my perspective, the beauty of lens design is that there's this interesting combination of science and then creativity to arrive at a solution. There are, of course, many base solutions, and we'll look at that in a few slides here, just a map of solution space as a function of field of view and an aperture stop size or F number. But this combination of creativity and science is really interesting, and what makes the science and art of lens design so much fun. So contrast optimization, as I mentioned before, is targeted. It is faster slightly, and I do not want to harp on the speed difference, although if you read the paper that was originally published by this, they claim a 10 times faster result than MTF, and that actually is true, but I've not personally ever used MTF only for my merit function. I've typically used RMS spot size or wayfront error or some combination of those things, or even other targeted ways to optimize the system. So while it is true it's faster than strict MTF, that's not really a good method to use to optimize these systems, which is why Zemax developed contrast optimization. And then the results are better. So the improvements in speed aren't really the point in terms of the ray tracing speed, but in terms of getting to a solution faster. So I wanted to make sure that that point was clear. So again, as I said before, we're going to skip to the end. We will look at the results, and then we'll talk about tolerancing a little bit, not with the system that I'm showing in detail here, but with another system, which shows the difference in speed or solution time, I should say, to arriving at a result for your tolerance system. So here we're looking at a table of the conclusion, really. So with image quality, I looked at RMS spot size, wayfront error, of course, contrast optimization, which is what we're talking about. And then I used some competitive software with the same base system to then do the optimization. And this comparison here, there are 3 target field points on axis, 7/10, and then the full field. And then just simply looking at the average of those numbers, thinking about that the image quality should just be an aggregate of all of your MTF. This is not an average of a large number of field points, but what's typically done in this sort of design. So the conclusion is this: we have nearly a 4% improvement over competitive software, but a larger improvement when compared to either RMS spot size or wayfront error. Of course, 2 built-in merit function, default merit functions available in opticstudio. Now, the speed differences we'll talk about next. This was on a 64-core computer, so it's quite fast. But if we look at things in terms of percentages, I think that's what's most important. Again, just make sure you jot down questions as we're going along here, as you're thinking about them, and we can address those at the end. So in terms of time, I didn't look at the 3 or 4 or 5 element system here that we will review in detail, but I looked at a more than 30, nearly 40 element near-infrared industrial borescope design I had done last year to understand if the use of contrast optimization as the default merit function would provide faster results for doing a multi-element, large number of tolerance operands analysis to then show is it worthwhile to then use this method also for multi-element systems when you're doing your final tolerancing. And the result was yes. So it was a 5 to 12% improvement in solution time when using contrast optimization, which is really, really important, especially for multi-element systems where you have a lot of variables and you're looking to do statistics and run a lot of systems. Now, this particular design, it was only being built for a few, but I did 100 Monte Carlo runs just to understand what the result was. So with that said, we'll look at some examples here. As I approach this topic, trying to put some numbers on contrast optimization, I looked at the time I was working in the medical field, and was designing a lot of these micro imagers for medical use, but there's other uses such as military and so forth. I then expanded that objective lens to just one or two relays, just to understand, is there a difference between more elements, multi-element system, versus just a few for the initial objective. Also, through this, I thought about, well, workflow and time savings and performance improvements, which is really what contrast optimization does. The workflow in any lens design, is important to think about the things that take you time. And as I was doing the tolerance work on that multi-element system, I was using some scripts to extract data from the merit function to then use that data to do statistics on the system to give a better view of the results and the sensitivities. And I've got a slide here towards the end which just shows that. The point is simply this, that it's good to investigate optimization and other techniques, but also to consider overall workflow and what is eating up your time in arriving at a solution, to then think about how to improve the overall time of your project. So with that said, I've just constructed here a high-level set of requirements that I used to make this design, and this design was from scratch. There's nothing proprietary here. Of course, the techniques are built over time and experience, as you'll see. But I was looking at a very small objective lens, and again, this was from a previous company doing a lot of this kind of work. 80-degree field of view, f5 system, no more than 2 millimeters diameter lens. Had to be a very small system. And then looking at 100 line pairs per millimeter with about a 5 micron pixel, using the Nyquist limit to get to that result. And the image size is consistent with image sensors of that caliber in terms of resolution and also the size we needed. And then being medical, there's also the need to include things like diagnostic filters. So there's provisions for that as a separate filter that would go into the system. As I mentioned at the beginning, the starting points of any of these lens designs is tricky. There's a program from Kioptique that's pretty clever. It's a first order program that gives a table, a kind of bubble graph of different types of systems on a X and Y axis of F number and field of view. And with this, if you plug in the results from this previous slide here, you can see the red cross where it ends up. We should either do a retrofocus or an Agilon or orthomatar or a Tessar, double Gauss. That's all in this sort of section here. The design that I chose, although I've got 4 different solutions that I could start with, I ended up using this plano concave start with the aperture stop and then the plano convex and a doublet. You could almost call that a retrofocus in a sense, but anyways, this slide here is to show that the starting point is so important. Once you get a design that works pretty well, then you can take that and modify it for field of view or F number or image size or anything else. But having that starting point is so important. One thing I didn't mention was the length of this system. Typically, there's no length constraint, and I said that here in this set of requirements. I did not constrain the length. When the diameter is so small, typically the length is allowed to be longer. So that's why the retrofocus works nice. It tends to be longer, especially with this option 3 with the 3 different elements in the stop internal. So here's the starting point, this retrofocus type arrangement with these 3 elements plus a diagnostic filter here as the last element is a provision. And the optomechanics, likely this would be all a compression fit. So you would load up the lens elements, the aperture stop, which could be placed even on the plano surface of this plano convex lens, the doublet for color correction, and then this could all be in one barrel with a compression fit, an adhesive bond, or retaining ring to load it all together. I've mentioned some things here like when you have the loading of the system from one side, you can control the diameter very accurately. Maybe use some two-part curing epoxy to hold the elements in place, and then you can make very thin beryllium copper aperture stops, which can be very accurately created to have the right size so that you control your F number, and of course things like straight light. So looking at RMS spot size, which is typically a good starting point here, you can see the layout, the result of the system. You can even take the data and reverse engineer it if you want to look at it yourself. And then the MTF plot here, just looking at the limiting spatial frequency of 100 line pairs per millimeter, we are achieving 55% modulation as an average. I did not do the tangential and sagittal separately, but just looked at an average. And then wavefront error, so same thing here. It's a little bit better than RMS spot size. We are getting 58% modulation at 100 line pairs per millimeter. And just to say, both of these, and also contrast optimization, and also the competitive solution, were all from the same starting point. So I did a little bit of pre-design work to get the system looking fairly good, and then use that as the baseline for optimization of all these systems. And then contrast optimization, which is of course the focus here, is 63% modulation at 100 line pairs. And I'll go back and forth between these slides, and you can see the difference in the systems. And it's interesting that as you set up these merit functions, and there's some control on spacing and diameters and other things as well that are built into the merit function. But again, just focusing on image quality here, you can see that that these are fairly different. And I did not expect to have this much of a difference in radius of curvature and spacing and thicknesses and so forth. But this is how it worked out. And then lastly, just to be fair, I am using RMS spot size control here, using some competitive software to Zemax opticstudio, and you can see the result here actually was pretty good. So that was good to see. Good to see, of course, our stuff win by a slight margin, but the other software is quite good. So wanted to be fair in the comparison. And again, just to reiterate what we talked about in the beginning, kind of results and conclusion before we go through the details, that contrast optimization does provide a benefit in performance. And I mentioned this in the very beginning, but what I did find going through this was that the time to arrive at a solution was less when using contrast optimization. And it wasn't because it was slightly faster in ray trace speed. It was more that I was able to get a good result using this default merit function than with previous methods. And then I added relays to each of these methods just to see what that would look like here. And I'll go through these somewhat quickly just to show the differences here. You can see here I've got different results in the sense that I'm reporting both on-axis and off-axis percent modulation at the 100 line pairs per millimeter cutoff. So 25 and 37% for RMS, 19 and 37% for wavefront error. And it's really interesting, the system design looks very different. The wavefront error result kind of shortened things up. And again, I use the same basic merit function script for all of these, just changing out the image quality metric in control. And then looking at contrast optimization, and if we compare that to some of these they look about the same between wavefront error and contrast optimization, but I get 19 and 37%, and I get 46.5% here with contrast optimization. So it's a very good result, and that's at the off-axis field point. So looking at the system adding the relay, then the results again are consistently better with contrast optimization. I'm sorry, that was the on-axis level at 46.5. So again, looking at the average of the 3 field points, the average result was about the same here between RMS and wavefront, and contrast optimization was quite a bit better. So again, jot your questions down. We'll collect those and talk about them here in a few minutes. I mentioned in the beginning about workflow in general, and this slide, a lot of detail here, but it just shows the use of the script, which is in this kind of yellowish or tannish highlighted thing over here, which will interrogate the tolerance, saved tolerance files. So it's all of the operands for tolerancing that are put in on the simple systems. You might have maybe 50, but on a multi-element system, you'll have hundreds of operands. So you can run your tolerance study, however many runs you save off. You can write a script to then interrogate that, look at your merit function, extract that data, put it into a text file, which is shown here in the middle, and then look at that later. And just a nice shout out to the community. I found this in a forum post. One other Zemax user had put the script together, and so this is not my original work. I'm happy to give this person credit for it, but it's very, very useful. I've saved many hours per design using this extraction method of data. And then really in summary, to be concise and precise here, when you're doing systems that have an image sensor, use this method. It works, it's effective. I'm showing real data here. It's practical. It arrives at a solution faster, maybe a few percent faster in solution time or in ray tracing time, but the solution time is quicker and better. So the other thing to make sure I point out again is that on the tolerance side, especially with complex systems, you have a faster solution than you would otherwise. So there's a nice cumulative effect when you're doing multi-element systems. Just a fun quote that I found, and this is how I've always operated, is that things should be practical. You should have defined starting points, defined endpoint, and if you can optimize your workflow, you can get to solutions faster. We've got a couple links here, which you will have this in the download. Of course, there's an e-guide you can look at, and then a webinar that talks about this that was a year or two ago as well. So those can be used for further reading. Of course, I'll have my contact information here. I'm happy to field questions after the webinar is over as well. Just send me a note. I'll respond quickly. I won't sell you anything. I'll just answer your questions. So really enjoy putting this together. Here's my contact information, and I think that is it.